Okay, so link here are that's the slide that we had with those structures. Can I explain more? Oh, okay. Yeah, so actually you're right about one thing. Connected graphs are not. Yes, it's a very good catch. I forgot to say of finite valence. This is a very good point, actually. Of finite valence. Meaning that every node has only finitely many neighbors. And that's important there, you're absolutely right. So without that assumption, the connected graphs won't be either algebraic or atomic. The lemma says that if they are algebraic, they are atomic, and these are algebraic. Once you have parameters, these are, I was mentioning, they are existentially atomic or existentially algebraic over parameters. So if you have a connected graph and you choose an element, then, and if the graph has this property that I didn't mention before, that's why probably you were confused. There are only finitely many nodes at distance 1, finitely many nodes at distance 2, finitely many nodes at distance 3. So the graph is algebraic. Every element, for every element, there is a formula that says you're at distance less than or equal n17 or something. But it's only true about finitely many things and contains the element. So that's why these graphs are existentially algebraic. From there to show they are atomic, it requires some work. So that lemma listed over there it's not a trivial lemma. It requires a proof. You can read it in the first book, but yeah, it's not an immediate proof. Does that answer more or less your question, Suling? Okay, so an abelian torsion-free group of finite rank. So all countable abelian torsion-free groups. So torsion-free means that every element, that there is no torsion elements. So for every element in the group, if you add it by itself any finite number of times, you never go back to 0. I'm doing additive group because it's an abelian group. So if you add it to itself, then you actually you get always new elements. Abelian torsion-free groups are always a subset of the group that you get by getting countably many copies of the rationals, like doing a kind of like the vector space of dimension infinity over the rationals, kind of like q to the infinity. So I guess this the omega sum or the sum of countably many copies of the rationals. That is a torsion-free abelian group, and any other torsion-free abelian group embeds in that one. And you say that a torsion-free abelian group has finite rank if it embeds into a finite sum of copies of the rationals. So that's what finite rank means. And these groups can still be quite complex. So yeah, there is work of Simon Thomas on seeing how complex these are from a descriptive set theoretic viewpoint, and they get more and more complex as n grows. But in this sense, they are not that complex because essentially once you have a basis, kind of, it's not a basis, it's a group, but something like a basis. You can generate all the elements. So every other element is not only existentially algebraic, but every element is definable from the basis in a quantifier free way. So then that makes them existentially atomic. So that one is, I guess, once you understand it, it's not that hard to see that it's essentially atomic. Make sense? Yeah, so it's a free, an abelian torsion free of finite rank means that you are a subgroup of a finite dimension Q vector space. So Q vector space is a group under addition, and it also has vector multiplication. Forget about the vector multiplication, consider only the sum. So a Q vector space is a group if you consider sum. So an abelian torsion free group is a subgroup of that, but it could be quite rich, these subgroups of Q, because like just rank 1, just if you look at subgroups of Q to the 1, there's a lot of subgroups of Q to the 1, depends on, so the integers are 1, but then you can take, for instance, all the things that are multiples of 1/3. They're also a group, they look like integers, I guess. But then you say all the elements whose denominators is an power of 2, the dyadic rationals. This is a subgroup of the rationals. So there's a lot, they can be quite rich, the subgroups of rank 1, and then once you start looking at rank n, it gets a bit more interesting to classify them. Yeah, so that's what it means. It's somewhat like having finite dimension for the group, except that they are not vector spaces because they're not closed under multiplication by all the elements of group of Q. I guess an abelian group is like a Z module. So Z is not a field, so it's not a vector space because Z is not a field with integers instead of Q. So Q is the most you can get. So they are, yeah, so with parameters, I guess I didn't write it down. I said when I said it out loud, I was saying that for this you need parameters. And if you choose parameters within the group that form a basis for the Q vector space, then you can show that even in the language of only with addition and without multiplication, you can still characterize every other element of the group using the elements of the basis as parameters. So they are algebraic over a tuple of parameters. Therefore, they are essentially atomic over a tuple of parameters. But they are not algebraic on themselves. No, probably not. Cool. Were there more questions in the review session? I really wonder what happens to the emails that you sent, because okay, so were there other questions, Richie, from the review session?
I think no more.
Okay. Are there any other questions from the students that we could take a look at now? Or from Jan, or from the professors? And okay, was there anything in particular you'd like me to go over? All right.
Okay. Okay. I think we can start. What about?
Well, we can start then.
Oh, I think some student has posted ask about the algebra over prime subfield.
No, okay, so the question is whether we need to parameterize over the subfield. No, in that case, we don't need to parameterize because the subfields are either ZP, like the finite field of size P. And then once you have the one, every element can be written as, every element in ZP can be written as 1 + 1 finite number of times. So you know, you can identify all the elements of the subprime. And then, so those are the ones that you need for your coefficients for the polynomials. And so that every element in your algebraic field is a root of a polynomial whose coefficients are in the subprime, in the prime subfield, but then those are the final. And the same when you have the prime subfield is the rationals, because in that case, also, well, it's not, you don't have a term, but every element is kind of like m over n is the unique element that when you multiply by m, you get n. So you can write that as with sigma 1 formulas. So every rational now is definable, I guess, in an existential way or quantified free way. So you can still write for every polynomial or the rationals an existential formula that says that you're the root of a certain polynomial of the rationals without parameterizing anything, just using 0 and 1 and multiplication and addition to name everybody. So no, in that case, you don't need parameters. Algebraic over the bound free. If you want to add parameters, you could say, well, now you can extend it to fields of finite transcendence degree over the prime subfield. And then again, if you put a basis for this, a transcendental basis, then you're algebraic over the basis, and then same thing holds. Okay, so the plan for today was the following. I wanted to show this theorem that we left from yesterday, which we used it a lot. And then I wanted to go and talk about the topological versions of Scott rank that we mentioned before. So Richie told me that that background, maybe people didn't have all that background, so we can go slower over the background that as I told you 3 days ago about the topology of bare space, and again, I can go as slow or as fast as you think is necessary. I think it's still a very cool thing to go and understand the topology, and then do the proof that I mentioned also that I left, that if you are uniformly computer categorical, then you're existentially atomic, effectively existentially atomic, and how that relates to Scott rank is equivalent to having a continuous isomorphism function. So the connection of all those things. And then just look at how the next few levels would work. We won't do the proofs. So that will be the objective. Let's start with with the back and forth relations. Just one theorem which is left. I don't know how you guys did proving this back and forth. The exercises from that we mentioned yesterday, they all take a little bit of work, but I guess the goal with the exercises is for you guys to see that it's just a little bit of work, but it's kind of like it's work that works always. It's kind of, you can do it. So you have to just keep track of many things, but it's a combinatorial thing to understand these back and forth relations. And that tells you a lot of information about the pi alpha sentences or formulas that are true about tuples or not, and if there are simpler ways. So we use this, for instance, to show that the Scott rank of omega to the alpha is 2 alpha. So that means we show it to prove that you need a Scott sentence for omega to the alpha needs to be pi 2 alpha plus 1, and there cannot be a simpler one. right? So that's one of the few ways to show that there is no simpler formula that describes omega to the alpha, for instance. The back and forth relations are used in the book, if you continue reading at some point, a lot more, because so there are many proofs, or I guess I don't know if many, but at least many proofs that that are more abstract, that are about structures in general and about what they satisfy, and the combinatorics of the alpha back and forth relations are very good for many of these proofs. So they are quite useful as a technical proof also. I guess we're not going to see that today, but just telling you that they do show up quite a bit, and they are kind of a natural notion. Well, as you guys can guess. Okay, so let's prove this. It's not. It shouldn't be super difficult. Let's copy it. Okay, the theorem says, so you're given two structures A and B. Let me choose my notes so I can read my notes. You're given two structures A and B, and the theorem says that A is less alpha than B. If and only if the pi alpha formula is about A, every pi alpha formula about A is true about B. So let's do that. So of course we use transfinite induction. So that means that we assume that this is true for all betas below alpha. Okay, so let's prove this direction. Okay, so take a pi alpha formula true about or of A. And we want to show that it's also in A. And we want to show that it's also true about B in the structure B. So this formula is pi alpha. So that means that it's of the form. What are the pi alpha formulas? It's an infinitary conjunction over some set of indices of formulas of the form for every y phi I x y. I guess the length of the tuple y variables depends on I. I'm going to simplify the notation. And where these ones are sigma beta for beta less than alpha. Right? So that's a pi alpha sum. Okay, so we want to show let's call this whole thing something phi of x. To show that B satisfies phi, what do we need to know? We need to show that it satisfies every one of these phi i's for every y. So okay, so what do we need to say? So take an I and in the natural numbers, and take a D in B. So these are the witnesses for this and for this. Yes, and we want to show that B models Ci be a D. right? If we manage to show this for every I and for every D, that shows that this whole formula is true in B. So far, so good. Okay, so how do we do that? Well, this formula here is sigma beta, right? So sigma beta I guess the beta depends on the I. So this one is sigma beta. So now what we're assuming that we know, this you're proving this direction. So we're assuming we know this, right? So this, so since this proves this, since we have this relation, we know there is C bar in A such that A C bar is greater than or equal beta B D. Right, that was the definition back and forth. But now since A models phi of A, so that means that for every I and for every Y, phi I is true. A models phi I of A comma C, because this is true for every C and for every I. Right? Now, okay, so now let's see what we know, and let's apply the induction hypothesis. So induction hypothesis is that from here we can deduce that every pi beta formula true about B and D is true here, right? But that's equivalent to saying that the negation of every pi alpha formula that is true here is also true here. It's just the contrapositive. So the same thing as saying that every sigma alpha, sigma beta formula true here is true here. Yeah, so in the case of sigma betas, it goes to the other way. So this is, let me just write that down up here. So this is the same thing as saying that the sigma alpha type of A in A is a subset. These going the other way. Right, because these are the negations. The sigma alpha formulas are the negations of the pi alpha formulas. So that means, so from here, you and here, you get that B models phi I of B. Yeah. Cool. So if you're good, we can prove the I direction. Okay, so for the I direction, suppose A is not alpha below BB. So we want to find a pi alpha formula true of A but false of B. Correct? So how are we going to do that? Let me just go to the next page. That's what I want. So how are we gonna do it? Again, it's transfinite induction, right? So this here implies that for every implies that there is D tuple D in B and a beta less than alpha, such that for all C in A of the same length, we have that C is not above B, D. Right? That's the definition of the back and forth. But then, by the induction hypothesis, we know that for each such C, there is a pi beta formula let's call it phi sub C of x comma y that is true of BD but false of AC. Right? So that is it's true here but false here. So then what do we get? So then we consider the correct formula here, right? The correct formula will be for every y that exists a C in A such that this formula phi C is false, is true of A in A. Why is that? Because for every in A, if you are in A, every y that you take is gonna be some tuple C. So it's gonna satisfy the negation of this one for that C. But it's false of B in A. That's because these formulas are true about D. So if you choose in B, if your y here, as your y you choose D in B, then all of these are false. So I mean, these are all true. And if you look at the quantifier complexity of this formula, okay, so this one is pi alpha. So this one is, sorry, pi beta. This one is sigma beta. And then the whole thing, sigma beta. And then whole thing, pi beta plus 1, in particular pi alpha. Make sense?
I think the whole disjunction is it sigma? I mean, is it sigma beta? Is every phi C is a sigma beta?
Every phi C, right? So every phi C is pi beta. When you take the negation, it becomes sigma beta. And then a disjunction of sigma beta is still sigma beta.
I think, I mean, is it for a fixed state?
For a fixed beta, yeah, actually, yeah. So actually you get, here you get beta plus 1, which in particular is pi alpha because beta is below us. Yeah, so I guess one observation you can to get from here is that if alpha is a limit ordinal, and you have this is true, then there is a smaller ordinal, such that this is true too. Namely, this beta plus 1. So the non-equality can, for the first time, cannot happen at a limit ordinal, it has to happen below. And that's true, that follows from here. Cool. Any questions? Okay, so if there are no questions, I'd like to switch now to topology on the space of structures. So a lot of notes. Okay, so let's remember a few things. So this guy up here is the set of tau structures with domain the natural numbers. Yeah, you guys remember we did this. So just to simplify, let's assume tau is relational. So meaning that there are no function symbols and there are no constant symbols, there are only relation symbols. You can always transform every structure into a relational one by instead of looking at the functions, considering the graph of the functions. The graph of a function is a relation that determines the function. Changing that could change a few things, but from the viewpoint of whatever we are doing, it doesn't change anything. So we're really not. This is not an assumption that restricts us in any way. You can always just change your function symbol for a relation symbol for the graph, and everything works the same. The same if you have a constant symbol, you can change it for a relation symbol, such that the constant is the only element that satisfies it. Everything works the same. It's just that the definitions and some things are easier and cleaner, and I have to consider less cases in the relational case. So let's assume that just so that we don't get bogged down by small details. Okay, so every and of course it's a countable vocabulary, right? So tau, by the way, tau was a vocabulary, right? Tau is a set of symbols that we are dealing with. It's in the first book, so I don't know if you guys remember or saw it. So for every A in a structure with domain omega, with domain natural numbers, we define D of A is the atomic diagram which belongs to the N is the atomic diagram of A. So I don't know if everybody remembers, I mean, or not everybody was in when you did the course, right, Richie? When you read the first book.
I think not ever have read your first book.
So let me define what that is. So D of A, D for diagram, is a sequence, it's an infinite binary sequence in 2 to the omega, such that the value at N is true, is 1 or 0, depending on whether A satisfies the nth atomic form sentence. Well, formula. This is the nth using constants for the elements. So let me explain this a little bit. So when you look at the diagram of a structure, you usually name all the elements on the structure. In this case, our structure has domain the natural numbers. So once you have domain the natural numbers, it's a standard way of naming the elements, given 0, 1, 2, 3. Those are the namings for your elements, right? So when you consider the atomic diagrams, you look at formulas or sentences about those elements, right? So for instance, you can say something on the form 3 is related, okay, maybe 3,7,8 belongs to the relation in the structure A. So R is a ternary relation in the structure. In this particular presentation, the tuple 378 might belong to the relation or not. So this is an atomic relation, right? It's an atomic formula, whether something belongs to a relation or not. I guess atomic formula in this case, you will write it as R of this. And 0 if not. Right, so the atomic diagram in general is a set of all the atomic formulas that are true about a structure, naming its elements. So it's a set or a binary sequence, saying 1 for true and 0 for false. And essentially it just contains information about what relations are true in which tuples and which relations are false in which tuples, and that's it. Okay. So and a structure is a structure in this guy of tau is determined by its diagram. So the diagram contains all the information about the structure, which relation holds about which tuple and which doesn't. Okay, so there is really no essential difference between the structure and its atomic diagram. They're kind of like the same objects, kind of. So essentially, we have a bijection. So D is kind of a bijection from the space of tau structure with domain n and 2 to the n. This is a bijection. So 2 to the n, that is called Cantor space. Has a natural topology. And I'm gonna say what it is in a second, but the idea is that then the space of structures inherits the same topology via this bijection. So the topology on this one is such that this bijection is a homeomorphism. It continues both ways. So something is open on one side if and only if the pre-image is open on the other side, and back and forth. Cantor space is called Cantor space. This is as a space isomorphic to the Cantor, like a 0-1 set. You have seen the 0-1 set that you start with the intervals and you remove the middle third, and then you remove the little middle thirds, and then remove the middle thirds, and you end up with this fractal. Has the same topology as this set here, and is the one that we mentioned. Has a natural topology where the sub or with sub-basic open sets being of the form of this form. And I'm going to take a pair n, 0. I'm going to define this thing and n, 1. This is a set of all x's in 2 to the n such that x of n equals 0. And this is a set of all the x's into to the n such that x of n equals 1. Okay, so a sub basis of open sets means that every open set, you get a basis of open set by taking finite intersections, and then you get all the open sets by taking unions, arbitrary unions of finite intersections of these guys. If you've seen these things below. So essentially, if for a finite function p from n is finite, partial, from n to 2, we let p is a set of all x's in 2 to the n that are compatible with p. Then the set of all p's forms a basis for the topology. So these are essentially these guys. A P with a finite domain it means that for finitely many natural numbers, you decide whether you choose a 0 or a 1. So essentially, you're taking a finite intersection of these guys. So these sets P are just finite intersections of the one before. So they are the ones that form a basis of open sets. And then every open set is just a union of these guys. So far so good. Is it too slow, or is this everybody, or is this a good? We're going at this. I don't know if everybody knows these things or not.
It's good.
Good. Okay. So now we want to. So we say that the topology here comes through here, comes from the topology here via this bijection D. Okay. So this the basic open set. Let's change colors. N, 0 corresponds in the space of structures to all to what set? I want to just write it down first, to the set of all structures in here, such that the diagram of A, when you apply it at n, you get 0. So that is the same thing as the set of all A's, such that for all in tau, such that A models the negation of the nth atomic formula. Because that's what it's actually, that's exactly what it means that the diagram is 0, that you model the negation, right? 0 means that you model the negation. This is not true of the nth atomic formula. Cool. And then also, if you take a P like that one, a partial finite function, this corresponds in psi tau to the set of all structures or presentations of structures such that A models, and I guess it's hard to say, well, okay, so I have to take the conjunction, it's a finite conjuncture over all n's in the domain of P of the nth atomic formula, but depends if P maps it to 1, I want to put the atomic formula. If P maps it to 0, I want to put the negation. Right? So I don't know how so I'm going to write that as P to P of n. By that I mean if Pn is 1, then just keep the formula. If it's 0, put the negation. If you guys are fine with that. Right? So if it's 0, I want to put the negation. If P maps n to 1, I want to put the formula itself. And this is up here is quantifier-free formula. That uses the constant 0, 1, 2, the natural numbers is constant about the elements of the natural numbers. Okay, so the set of all A's that satisfy a certain quantifier-free formula, these form a basis for the topology. Okay. So what's the good? So what are the open sets? So the open sets in X tau are unions of these guys. So that means they are the form all the A's inside tau such that A models this junction. So one of phi, where each of these guys is quantifier-free formula, is one of those. Let's not call it phi. Let's call it something else. Let's call it psi I, because it's not. These are conjunctions psi. This is like the full thing. So this junction of this quantifier-free formula is one of those. And in general, if you also have an existential, you can replace an existential by this junction. But it's like a union of things. One of these things is true. So I guess one observation for every infinitary sigma 1 formula, which includes also existentials, the set of all A's in chi tau such that A models C is open. Okay. And then by infinitary 1 corresponds to closed, because it's the complement of open. And then by 2 infinitary, this is an intersection of open sets, because it's an intersection of sigma 1. So this is what is called like a G delta set, essentially. Or by 2 in the Borel hierarchy. So let me just go back on to one of the slides where I define these things. If you guys remember, the Borel sets are defined by taking countable unions, countable intersections of open sets. And actually, you can go through the transfinite taking these countable intersections. And we define the first class these hierarchies of Borel sets, where the sigma n ones were defined as unions of intersections of unions of intersections, n alternations of starting with Kloppen, I guess. sigma 1 is the same as open, pi 1 is the same as closed. That's what I just said. Pi 2 is the same as G delta. So this is a different hierarchy. This is not a hierarchy. This is not formula. It's not formula. It's a hierarchy of sets in the Borel hierarchy. They use the same notation of sigma n because they actually match, but the definitions are very different. So I guess the observation is that if a formula of, let's say, phi is a sentence, is a sigma infinitary sigma alpha sentence, then the set of all A's in K tau such that A models phi is boldface sigma alpha in Borel hierarchy. In terms, can be written as a union of intersections of unit intersections of Kloppen sets. And that's not hard to see. That's just because every disjunction becomes a union, every existential becomes a union, every conjunction becomes an intersection, and every for all becomes an intersection.
I think we have questions in the chat box. Sulen, you can just speak up.
Now I can see your face, Sulen. Yes, parameters in the formulas. Yes, so here we allow. Yeah, so these formulas allow parameters from the natural numbers actually. Yeah, you can use any parameters you want. For at least for this observation here, you can use parameters. Okay. One thing I mentioned these Kloppen sets. I say these guys are the basis of the topology. They are, I was saying, they are open, but the complements can be written as the union of everything that is not, that makes P false. So the complements are also going to be open. So these guys in this topology, they are not just open, but they are closed also, because the complements are unions, basic open sets, everything that makes this false. So, well, essentially, this one is a complement of this one. So if this one is open, this one is closed, and vice versa. So these guys are Kloppen meaning they're closed and open. So this is a special kind of topologies where we have a basis of Kloppen sets, not just open sets. Cool, and there is a very nice theorem, which I'm going to prove, due to Lopez Escobar. And I think this is in the 60s, that says that if we have a class of structures, it's a subset of the space of all structures. I need some more room for this. It's a subset of the space of all structures and is closed under isomorphisms so that means that if A belongs to K and B is isomorphic to A, then B belongs to K. Then, okay, is K is close enough, and this K is sigma alpha in the Borel hierarchy. So if you're given that the set is sigma alpha in the Borel hierarchy in terms of unions and intersections, then there is a infinitary sigma alpha sentence with no parameters. Such that K is the set of all the structures such as A models this sentence. Okay, so if you take the set of models of a sentence, then it's going to be closed under isomorphisms because, right, so the truth of a sentence is independent, it's closed under isomorphisms, right? That depends only on the isomorphism type. This is a very strong theory, and it means that it can go all the way, or the other way around. So if you have a set of structures that is closed under isomorphisms, and that is sigma alpha in the Borel hierarchy, then there is some sentence describing it from the inside. So it's quite, I mean, if you think about it, the two things are quite different, right? Because this is sigma alpha in the Borel hierarchies, define the structure is a class of structures, and you define it from the outside, taking units of intersection. And this is something from the inside, which is writing a formula, and you're seeing whether the formula is true about A inside or not. So in that sense, it's quite different. Okay, so that theorem, the proof requires forcing, which it will take some time to develop. So I wanted to go into that. This is what we need. That theorem is what we need to show that these two are equivalent. So the equivalence of these two things is all. That's not is that the set of copies of a structure is pi alpha plus 1 in the Borel hierarchy. Is the same as saying that A has pi alpha plus 1 Scott samples. So the fact that those two are the same is a direct corollary of that observation that we just did and of the theorem of Lopez-Escobar. So these two things are in parallel. Good. Another thing to mention here, which is the question that Liang asked some time ago, is why do we define sigma, the complexity that way? Like, why is that we, I don't know, well, in this particular case, why is that we group these junctions and their x's, and we put all the x's together, and then we group these guys, and then we group these guys, and we count ternations. And the answer is that because that's, if you define the complexity that way, then you get this matching thing between the Borel hierarchy, the topology, and the infinitary formulas. That's when you find them to match. So that's the good complexity to do that. Cool. Okay, so let's now look at this other thing we were talking about. Where is it? There was another way of defining the bare rank, which is just one I mentioned in the case alpha equals 1 and maybe alpha equals 2, which was the bare rank was the least alpha such that A has an isomorphism function of bare rank alpha minus 1. What was that? So an isomorphism function for a structure A was a function that given two copies, so two copies of A. So these are two presentations of A. They are isomorphic to A, but they are different representations of A. Then the function with that input will output an isomorphism from one to the other. So we know they are isomorphic. The question is like how difficult it is to find this isomorphism. So the isomorphism function gives you this isomorphism. And the measure we had for the complexity of this isomorphism function was this bare hierarchy. And the bare hierarchy was the level 0 was continuous. These are the continuous functions. and beta class alpha was pointwise limits of functions of previous rank. So beta class 1 means you're a pointwise limit of continuous functions in particular. Okay, so let's try to understand what it means to be, let's start by continuous. So again, the space of structures is the same as Cantor space 2 to the omega. So let me just write this theorem, and let's then discuss how much we want to go into details. So 2 theorems I'm going to write. So consider a function gamma from 2 to the omega to omega, let's say omega to omega. That's omega. The following are equivalents. One is gamma is computable. What does it mean that a function from 2 to the omega to omega to omega is computable? Here's a definition. There is a Turing machine I don't know what you call it, M, such that for all x in 2 to the omega and all n in omega to the omega, the value of gamma at x, which should be gamma at x should belong here, is a function from omega to omega. So the value of gamma at x at n is the output of M using oracle x and input n. I imagine people are used to a machine with an oracle. Yeah, so you have a tape where that's the. Okay, so that's what when we talk about functions from here to here to be computable, we just say that we put the value here in the oracle tape, and then we get a function here that given n gets that up. So that's a continuous function from the reals to the reals, and that is equivalent to saying that there is a computable function f from 2 to the less than omega to omega to the less than omega. So these are finite strings such that for all x in 2 to the omega, gamma of x is equal the union of all the strings that correspond to. So take all the initial segments of x, these are finite binary strings. They are all nested, they are all like nested in each other, and the union is the output. Okay, so this function satisfies that if sigma is a subset of tau, then f of sigma is a subset of f of tau. So it maps kind of this binary tree into this other tree in a nice way, in a coherent way. And if you go through a path on this binary tree and you look at the images of that path, you're going to get this function. All right, so being computable is the same thing as having it. How much do you guys know this? And or how believable is it for you guys? How much detail should we go about it?
I think it depends on how much we could see.
Okay, we can go forward so we don't spend too much time in saying.
Yeah.
Okay. Let me write another theorem. Who is to be? Okay, it's a bit smaller. Let me I'm going to change this theorem a little bit. I'm going to put a third condition, which is f is continuous. So we have a topology on here and on here. That's the same as we defined before. So we know what it means continuous. The pre-image of an open set is an open set, or the image of a limit is a limit of the image. We know that. That's not equivalent to what we just wrote. We need to change these things. So there exists a Turing machine M and a set Y, an oracle, such that for every n, so what the output of this function on X input n is the output of the Turing machine M using oracle X together with Y. So we put X and Y together and input n. So we have a fixed binary sequence that we use as parameter in our Turing machine. And then here, which is erase this part. Okay, so these three things are equivalent. So being continuous is the same as being essentially computable relative to some oracle. So it's computable by you're using some oracle, fixed oracle. And it's the same thing as there exists such a function. But now you don't require the function to be computable. Okay, so that's the connection between continuous functions and computable functions. Just in the continuous case, you're allowed to use any oracle you want. In the other case, this function has to be, in the computable case, this function has to be computable. And if you want to do the proof, essentially what happens is that this function here is your oracle that you add here. And then so from 3 implies 2. You just need, the proof of this is just writing down the epsilon delta definition of continuous and seeing that continuous for a function like this. A function is like this continuous if for every x, if you want to know an initial segment of f of x, all you need to know is an initial segment of x. There's an initial segment long enough that is going to determine the value of f of x up to a certain point. Yeah. So maybe, let me write that down because that's kind of nice. So continuous. If you write the epsilon delta definition in this metric, this is the same thing as for every x and every m, there is an n such that f of x up to m. So if we want to find the first m bits of f of x, this is determined. Oh, the term, I cannot write that. By x up to n. So you only need the first few bits, well, some many bits of x to determine a finite amount of f. This n might be much larger. This n might be much larger than n. And essentially, if you do the epsilon delta definition, this m is the 2 to the minus m is the epsilon, and 2 to the minus n is delta in the usual distance that you put on this space. Okay, so that's the topology for that. And then if you look at that theorem again, where is it? No. Okay, so the Bell rank is the least alpha such that you have an isomorphism function that is Baire class alpha minus 1. So if the Baire, you have a theorem that says that the Baire rank is the same as the Scott rank. No, that one. Right, so having Scott rank alpha is the same as this an isomorphism of Baire class alpha. So if alpha is equals 1, case of alpha equals 1, what this says is that A has Scott rank 1 if and only if A has a continuous isomorphism function. And an isomorphism function is a function that, given a structure, gives you the isomorphism with the structure. All right. Now, Scott rank 1, this is the same as A has a Scott family of sigma 1 formulas. And a Scott family, I don't know if you guys remember from yesterday, is a set of formulas defining all orbits. Right, so all orbits are definable as sigma 1 formula, the same as Scott rank 1. So if you go through the effective version of this, so this is the same thing, and this whole thing. So having a Scott family of sigma 1 formulas, that implies you have a Scott family of sigma. This is the same thing as saying A is existentially atomic. This is what we mentioned before. Now let's look at the theorem that we had yesterday, which is the effective version of what I just wrote. This theorem says that if that A is effectively existentially atomic, in this case over parameters, if and only if A is relatively computably categorical. And okay, let me write this theorem in a better way. So now we have this Scott rank 1, essentially atomic is the same as has the continuous function. The theorem I want to write is the following. A is effectively existentially atomic, which is an effective version of being atomic, if and only if there is a computable operator gamma such that if B is a copy of A, so it's another representation of A that is isomorphic to A, then gamma on input diagram of B is an isomorphism let's say let's do the same as in the proof that I need B to A. And again, here I'm assuming A is computable. So I don't need to put the diagram of A. And effectively atomic means A has a CE, computably enumerable Scott family of existential formulas. Okay, so being effectively existentially atomic is the same as saying that you have Scott rank, but in an effective way, in a computable way. You have Scott rank 1 in a computable way. And then this other thing is essentially, this gamma is essentially a continuous, a computable isomorphism function. So this theorem up here is kind of the computable version of this particular case up here. Okay. So we already showed the left to right implication. So we already show this. Now I want to show the other implication. So I'm going to copy this to the next slide. And we're going to do the proof after the break. So let's take a break, 15-minute break.
Yes, let's take a break.
So, yeah, any questions?
If no question now, then let's meet again at 45.
45? Cool. Okay, so this is a very different proof from what we've seen so far, and it's not a long proof, but it's subtle. So I want to go slowly through it, just so that you get a gist of how this proof. I mean, how is that you connect things? Computability property becomes a structural property, right? Because here what we're given for this direction, what we're given is this gamma that is the computable operator that maps structures into an isomorphism from the structure. And what we want to build is this family of existential formulas defining the orbits. Of all the automorphism orbits out of this computable operator gamma, right? So I need a little bit of notation, which is in the first book, but in this case you haven't seen it. So for notation, I'm going to define, if you have a tuple A within a structure A, this is going to be, this is called the atomic diagram of A in A. So this is a tuple. It's going to be a finite tuple. It belongs to the length of A. I'm going to just we could have chose another length, but it's just a finite tuple. And the definition is the same. So VA of A at N is going to be 1 or 0 again. And then this is if A models the nth atomic formula applied to A0. Well, this is the tuple, no, this is AK. Where, let me go back. When we define the diagram, where is that? The diagram, these formulas up here, the nth atomic formula, we're allowed to use these numbers as constants, because these are structures whose domain are the natural numbers, and these are formulas about the elements of the domain, right? So they're about 0, 1, the numbers, right? These formulas, like this one, R of this. Now, we consider the same enumeration, the same list of formulas, but now instead of putting 0, we put A0. Instead of putting K, we put AK, where the A0 is the first element of the tuple A, right? Tuple A is A0 up to AK. Make sense? So for instance, so if A0, A is the tuple 0, 1 up to K, the first K number, the first K natural numbers, then dA of A is an initial segment of the diagram of A, of the full diagram of A. Okay, but I'm allowing here other tuples instead of just the initial one. Good. And by the same, if we have, this is an important observation. So if G is a bijection, it's an isomorphism from B to A, then I guess it's an isomorphism. That means that the diagram of in B of the tuple 0 up to K, let's say K minus 1. The diagram of this tuple is the same as the diagram in A of the tuple G0, GK minus 1. It's because G is an isomorphism, so it just maps everything the same. Right? And now the diagram, the full diagram of B is the union of all these guys, right? These are all the initial segments of the diagram of B. So diagram of B, let me just write it better, is equal to the union over all K's of the diagram in B of the tuple 0, K minus 1, which by this equality up here is going to be the union over all K of the diagram in A of this thing, which I'm going to write as G up to K. This is the first K values of G. Okay, so I'm going to write that again. And diagram of B is the same as the union over all natural numbers K of the diagram in A of the tuple G up to K. So if we are essentially, if you are building B, for instance, using an isomorphism like this, from B to A, the diagram of B is determined by the union of the images of the first step as G grows. Good. Okay, so let's go into the proof now. So what do we have? We have a computable gamma that has the property that whenever you apply to a copy of A, any copy of A, you're going to output an isomorphism from B to A. And this diagram of B, if B is something that is given by, it's an isomorphic copy of A, so it's an isomorphism from B to A, this diagram of B is a union of all these things. Okay, and this gamma is computable, so that means these are initial segments of B, so this infinite function is to know more and more about this injection, this isomorphism, we need to know more and more about these things. So the finite initial segments of these isomorphisms are determined by the finite initial segments of these in such a B. Okay, let's kind of be more concrete on these. So this is the key observation here. So for any Q that belongs to A to the less than omega, it's a finite tuple from A. If gamma applied to the diagram of A in, of Q converges up to between 0 and K minus 1. Okay, so let me see what this means. So remember, this gamma is a computable operator, right? So one way of thinking about it is a Turing machine, and then this is the oracle, right? So this is the oracle of the Turing machine because it's a computable operator, right? So it's an infinite oracle. So that means if he instead of putting an infinite oracle, we put an initial segment, the Turing machine is going to converge on some things, on some inputs, because it's not going to ask questions beyond that segment. And it's going to start diverging when you ask very large questions about large inputs, because it's going to be asking questions about things that are not in the oracle. If the oracle is just finite, if you don't put a full oracle, okay? Or equivalent to what I'm thinking is if you have a computable function, if you only input a finite string instead of an infinite string, you're going to get a finite string out. Like that F that I was mentioning before, right? So here, this one is a finite string. Because this Q is a finite string. So if you input a finite string as an oracle, and suppose it converges on the first K values, then the automorphism orbit of this tuple Q up to the number K, which is how much it converges, is determined by the diagram of Q in A. What do I mean by determine? I mean, if P is another tuple, if you have another tuple P and the diagram of P in A equals the diagram of Q in A, so if you have two tuples that are like this, then Q up to K is isomorphic, automorphic to P up to K. That's what I mean by that. That's what I mean by saying that the automorphism orbit of this guy is determined by this finite binary string. But if some another tuple with the same finite binary string, the same domain, the same atomic diagram, then they're going to be automorphic. They're going to have the same polymorphism orbit. Why is this good? Okay, so we're going to see later why it's good, but just let me give you what we're trying to do. Remember, what we're trying to do is show that A is effectively atomic, which means that every orbit is definable by an existential formula in a computable way. So we need to find this existential formula that defines the orbits, right? So here we are saying that the orbits of these tuples are determined by something that is very finitary and depends on the diagram. So this is going to allow us to define these existential formulas later to define the orbits of these guys. Okay, so we need to prove this observation. This observation is not obvious at all. So to see this, we prove that, or we claim that Q up to K is actually isomorphic in the structure A to this gamma applied to the diagram of AQ up to K. So gamma is an isomorphism from B to A, right? So when I say gamma is up to K, I mean in the image, look at the image of the first K elements of B in A. Okay, that's what this means. To see this, so suppose G from N. Okay, so I'm going to define. From E to B bijection. We're going to assume that Q is 1 to 1, I guess, extending this tuple Q. Okay, so Q is a tuple of elements. Now continue enumerating all the elements of A, and we get a bijection. And let B be the pullback of this. So B a structure. I mean, but by this B, all I'm doing is, so we have these maps, this is a bijection between these two sets. Here we have a structure A. So just pull back all the relations from here through this bijection, and I look at the equivalent structure on this side, and we call that B, right? So B is a structure with domain N that when you go through G, you get isomorphism. So B is called the pullback of A, but it's the obvious thing. No, it's the unique way of defining the relations here so that they come through from here through G. And it's a bijection. So B is isomorphic to A. So we know that gamma with oracle DB is an isomorphism from B to A. So let's see what we have. Let me erase that. So we have A, we have an isomorphism, gamma dB, that goes to B. We also have the other isomorphism, G, that goes to B. Oh, sorry. This is the other way around. B goes to A, and B goes to A through both these things. Now, if you take the tuple 0, k minus 1, this is a tuple that belongs to here. If we apply, this is going to go to gamma of dB up to k, right? The first k bits of that. That's the tuple that corresponds to it. But now we're assuming this converges. So not so. So the diagram of Q in A is a substring of the diagram of B, because of this property. The diagram of B is the union of the diagrams of these maps that we get. And then this Q is an initial segment of G. So this one here is the same as the diagram in A of G up to the length of Q, essentially, which is an initial segment of B. And then the gamma already converges on this string. So we don't need to put the full string here. We can put diagram of Q. So that amount of oracle is enough to get convergence. And that's an initial segment of B, because we are assuming this converges. Now, if you go on the other side, G, well, here you get Q, and this maps to Q up to K. Okay, so that's how we get the Q up to K is automorphic to the image of this gamma, the first K values of the image of the gamma, if we know that this converges. And now once we know that, why is that we get our claim? Well, suppose this is the case, then what do we get? Then we get that Q up to K is automorphic in A to gamma using oracle D A Q up to K, but this oracle here is the same as D A P. That's our assumption right here. Up to K, and that's the same by what we just proved, that's the same as P up to K. So let's repeat what we have so far. So we prove this observation now. So if you have a tuple, and we know, and that we use a tuple as the diagram of the tuple as an initial segment of the oracle of gamma, and we see how much it converges, and it converges on the K first, in the first K element, then the automorphism of Q, that tuple up to K, completely determined by this tuple, by the diagram of that, in the sense that any other tuple with the same diagram, you're gonna get something automorphic, anything like this. All right. So now let's use this to define the orbit of Q. Okay, so now given a tuple A, in A to the less than omega. We want an existential definition of the orbit of A. So what do we do? So let Q be an extension of A. It's a tuple extending A such that gamma with diagram of Q as input A converges so it gives you an answer on the first A values. Why do we know if this is true, that there is such a Q? Well, if you extend, this is the same as we had before. If you extend A to an isomorph to bijection of the natural numbers to A, and we define a B the same way, we know this gamma converges must give you an isomorphism. So it has to exist such a Q. Always. Every tuple you can extend it to something that is like that. Make sense? What I'm okay, maybe I'll write it on a side. So you have so we let G from N to A extend the tuple A, and then we know the gamma diagram of, and we let B be again the same thing, the pullback of the structure A, and we know the gamma diagram of B is a bijection. Is total, so it must converge on some on at some point for it to figure it out. The first few values, we don't need the whole oracle, we just need a finitely much of the oracle. So that is a Q. So just see how much of this oracle we find. What is the diagram? And that is the tuple that we have up here that we need. Okay, so but we know now that every other tuple that has the same diagram as Q determines A. So so we know from the claim before that the automorphism orbit of A is determined by the diagram of Q. So just let sigmas of A, this, so find a binary string, be the diagram of this Q. So find a tuple. And now the formula that we're going to define, the formula that depends on X, is the formula that exists a Y extending X such that the diagram of Y equals sigma. So the claim is that phi A defines the orbit of A. So, okay, so what do I mean by diagram this thing? I mean, this has to be a first order formula in the language, the tau first order formula in the language of the structure. So sigma is an infinite binary string. And d of y is not well defined, but d of y is essentially given by certain atomic formulas being true or not about this tuple of variables y. Right, so we have the first atomic formulas. So this up here you can write as a quantifier-free formula. I guess I don't know if I want to go into details. I could do it in a side here. So this is a conjunction for I less than the length of sigma of the atomic formula, nth atomic formula, the ith atomic formula, applied to the tuple y. But then depending on whether sigma is 0 or 1, we want to put the formula or the negation. So we do this sigma at I, meaning if it's 1, you put the formula, if it's 0, you put the negation. So this is a formula that says that this tuple of variables y, the diagram of it is the same as sigma. It's just a conjunction of atomic formulas. So this is a quantifier-free formula. Cool. Okay, so why does it define the orbit of A? Well, you have to show two things. It's true about A. Why is it true about A? Well, it's true about A because what will be the Y in this case? So if X is A, what will be the Y? Well, the Y is Q. Q is a tuple that extends A, and sigma was defined to be the diagram of Q. What if this formula is true about somebody else? That is somebody else. Well, if there exists a Y extending it, let's call it P, a witness. So let's let me just write it down. So if phi A is true of some tuple B, there is a P, namely this Y, extending B, such that the diagram of P is sigma, which is the same as the diagram of Q. But then we know that from before that this implies that P up to length of up to this number. This is K. Is equal to Q up to K. But then this is A. And this is B. And sorry, automorphic. So if it's true about somebody else, it must be automorphic to A. So this formula is true about A and it's true of only of things that are automorphic to A. And that's the formula. And we can compute this formula. We can enumerate these formulas in a computable way, because if you have A and A is supposed to be a computable structure, finding a Q, extending it such that this converges, you can do it in a computer enumerable way. Just wait, start adding things and wait until you see a convergence. So that's computer enumerable. So we can find these Qs. Once you find these Qs, you find the sigmas, and then you write these sentences. So the family is computer enumerable. So that's how we get all the existential definitions in a computer enumerable way. Any questions? I know it's a bit convoluted proofs. Yeah.
I have a silly question. Antonio, I have a silly question. So can you switch the quantifier? This is computable for every automorphism to be, for every automorphism, there is a computable function.
For every, say that again?
So look at your statement, your and you said there is a computable function such that for every isomorphic copy, blah blah blah. Can you switch it to be for every isomorphic copy? There is a computable function.
Yes, no. Okay. I see your question. So, right. So this is a computable function. It's a single computable function that works for every copy. And what Yang is saying is, what happens if we, instead of saying that, we say that for every copy B, there is a computable function that is not fixed. Well, in that case, you will get a theorem, and the theorem is that it's equivalent to saying that A is effectively extensionally atomic over some parameters.
Okay.
So the direction from like it's the easy direction from up to down. If you have the parameters and you're giving a copy, you don't know where the parameters are, but non-uniformly you can find the parameters.
Okay.
And then once you have that, you find this computable function. So that you need to find the parameters non-uniformly. The other way around, you need a much more complicated version of this same proof that we're doing here to show that what you're saying. It gets a bit more complicated, but yeah, it's still a nice thing.
Okay.
So actually, that's the theorem that we had. Where is it? Last class, yesterday, that I wrote yesterday, was like that. I was saying A is effectively extensionally atomic over parameters if and only if for every B there is an isomorphism from B to A that is computable in B. So that was the version that I mentioned last time, but that's a bit harder to prove. This one is already, I guess, this one is not, I wouldn't say it's hard, it's short to prove, but it is tricky. You have to look at it a little bit to follow this proof completely. Any other questions? Okay, I'm gonna so there are more questions. I'm gonna show you how write down a theorem that is how this extends to the Scott rank 2 case. So remember that structure A has Scott rank less than or equal to Scott rank of a structure A. If and only if A has a Scott family of infinitary. This is just the last few minutes. So just to mention, find 2 formulas. Now remember, a Scott family is just a list of formulas defining all the orbits. So a computable version of these the following. Okay, so maybe we don't know how to say, we don't need to put the following. One, A has a computably enumerable, so CE Scott family of, sorry, the other way around. Of, and this is something I haven't defined, but this is computable. computable infinitary formulas. I'll tell you what they are in a second. And that's if and only if two A is uniformly delta 0 2 categorical. What does that mean? There is a computable gamma such that for every what they are, right? B that is isomorphic to A. When you apply gamma to the diagram of B, to the jump of the diagram of B, you get an isomorphism. So in the next level up, instead of having a function that is continuous on the diagram, now you're using the jump of the diagram. And the jump, that's why the delta 0 2. Delta 0 2 is because of the jump. Here, so for Scott rank, okay, so Scott, I wrote this column. Scott rank 2, I said you need infinitary sigma 2 formulas. Here, these are computably infinitary formulas. Computable infinitary formulas means that the disjunctions, you can enumerate the disjunctions in a computable way, and you can enumerate the conjunctions in a computable way. So it's not any infinitary formulas, but the ones that you can write down computably. That's not the ones that happen, the ones that we're talking about here. So this is kind of like having effective Scott rank less than or equal to. And now that's the same thing as having this thing. And now that's the case alpha equals 2 from the theorem, because these are the functions of Bayer class 1. I guess I don't know if I want to write it, but for gamma 2 to the omega, 2 omega to the omega, gamma is of Bayer class 1. So meaning it's a limit of continuous functions if and only if there is, so let's call it F. A computable function gamma and an oracle y that belongs to 2 to the omega such that F of x is given by gamma applied to x plus y jump. So Bayer class 1, like limit of continuous functions, is the same thing as formulas of this form. Something computable applied to x plus y jump. So those are the same things. And they are also, yes, we can. So that's how you get the connection between the theorem that we had before and this thing over here. And then this goes up. You can like this. You can go up the hierarchy and start doing the same thing when you go higher up. Again, this requires forcing. That's why I used to prove that equivalence. So it needs more techniques. Any questions?
Okay, so the proof is similar, right? The proof was about the bare class, and the proof that you have presented. There's actually similar.
No, it gets more complicated. So let me. The proof.
Yes, you have presented an effective case, right?
Yes.
And
So
bare class is
okay, no, but bare class 1, like, which is the level 2, it's got rank 2. So that the implication from 1, the 1 implies 2, is very similar to the one we did before. So if you have your Scott family, you can find this isomorphism. That's not hard. Going backwards using the jump, it's a bit more difficult.
okay, but the case bare class 0 is.
Oh,
is
for bare
essentially
class 0,
similar.
yes. So for bare class 0, right. So yes, yeah. So if
It's
here,
essentially similar.
if here you remove the effective, and here instead of computable you put continuous, then you get the same. You get a you get the theorem that is to say essentially the same proof will work. So this theorem will prove the case when you forget about the effective here, and you forget about the effective here and put continuous instead. So yeah,
Okay.
that follows from this case.
So why not X jump O plus Y? Why is the X O plus Y jump?
Because yeah, you need to use the jump of the parameter, I guess. Yeah, I think you need it. Yeah, you need it.
So in bare class 2, is it double jump or?
That's right. Yeah.
bare-
Bare class 2 is double jump. Bare class alpha is the alpha jump.
Okay. Good.
And bare class alpha is also the ones, like if continuous functions are the ones that the pre-image of every Kloppen set is open, right? Or the pre-image of every open set is sigma 1, that's continuous. Bare class alpha means that the pre-image of every Kloppen set is sigma alpha plus 1. That's also equivalent.
So the omega jump means you have the union of the previous jumps.
That's right. Yeah. Though here you have to be a bit careful, yeah, in spare class alpha omega. Maybe it's the next one up, but more or less, yeah.
So in the Borel hierarchy, the omega hierarchy is essentially the union of the previous hierarchy.
In the Borel hierarchy, the omega hierarchy.
Or the limit ordinal hierarchy. Is
Yeah,
the
so
union of the previous hierarchy.
yeah, so actually there is a mismatch in the notation in different things when you take the. So the omega jump is the union of the previous ones, but sigma omega doesn't mean that you're sigma n for a previous n for some n. It means that you're disjunction of things that are sigma n. So when you go to sigma omega, now the correspondence is with the omega plus first jump.
Yes, and actually
the Borel also becomes like that because it's the union of things at the previous levels. So there is an annoyance in the standard way people talk about the omega jump, and the standard people talk about sigma omega that they don't match, and the infinity case they don't match. So, but it's just a technicality that just to, I think the notation that you need to get right. So in the book I make an effort to get it right.
Okay, so only in the formula, in the formula case, the limit ordinal is not the union of previous ordinals.
Right, but in the Borel hierarchy also.
The Borel hierarchy, it is.
Like a sigma omega in the Borel hierarchy is a union. The set is a union of sets that are in the previous levels.
Yes.
Right.
Oh,
So that's
yes,
the same
so-
as the sigma. That's the same as sigma omega. So this junction of formulas at the previous level.
Okay, okay. It's interesting to find the difference between these definitions.
Right. Yeah. So it's like
Yes, and the back and forth relations, and when you define the back and forth relations,
yes, they are in that case they are the intersection of the previous ones.
yes, yeah, it is so only the formula case is somehow different from the others. The
Yeah,
others use
it just
union or-
yeah, but they just stand that way so that everything kind of works good. So the back and forth case, they are still related to the formulas.
yes, and still everything works well together.
Mhm.
Okay, thank you.
Anybody else have any more questions?
Do we have more? Do we have more questions?
Oh, so in the proof of the bare rank, it is you also in the higher ranks of the Borel class, you still need the concept of computability.
Yeah, they go through the concept of computability. Do you need it? It's a refined result using the computability. Let me think. Yeah, so the way the proof that I use is all using computability ideas, right? So you have an oracle, and the oracle is the whatever alpha jump of the structure. Yes, so so at least the way I know the proofs is by using the connection. Yeah, so instead of talking about beta class alpha, I talk about functions that whose input is the alpha jump of the oracle.
Okay, I think this is an interesting application of the computability theory to get a result that seems not related to computability.
Right.
In the
Yeah.
first review.
Okay, if there's no more question, I think that's it. Thank you all for participating in the summer school, and that's thanks to Professor Mokoba. And if you guys don't mind, would you like to show up and let's take a group photo?
Oh, finally see your face.
大家能不能打开摄像头？然后
No, nobody wants a photo.
no. Okay.
So Richie, you send me the videos and I'll send you the notes. I'll send you these notes right now.